Well, we're coming to the end of this course, and I'd like to spend some time reviewing what we've done. What did we learn? What are the most important lessons to take away? One of the most fundamental things we did was learn about sampling theory, the digital representation of continuous signals. This material is particularly important in computer music, but you find it also in studies of speech, in computer graphics, in image representation. It's really pervasive. The big idea is that you can represent every instant of a continuous signal with a finite set of samples if the signal is band limited. And in practice, quantization introduces noise, but every bit reduces the noise by a factor of 2, or about 6 decibels per bit. You should know how analog to digital converters work and how digital to analog conversion works, and you should understand the impact of sample rate and sample size on these signal representations. We talked about unit generators. Synthesis generally works by combining unit generators. Unit generators model processing on input signals to produce output signals, and unit generators have internal state. You should know how unit generators and connections are expressed in Nyquist, and you should also know how unit generators and connections are expressed in visual programming languages like Max MSP and PD. We studied the frequency domain. Our perception is mainly based on intensity at different frequencies, hence the spectrum. Linear filters are described as multiplication in the spectral domain, multiplication of the spectrum. And you should know how to interpret a spectrum as a sum of sinusoids, noise, etc. So in other words, peaks in the spectrum typically correspond to sinusoids, and energy spread out at many frequencies indicates noise. You should know how to interpret filter frequency response expressed as a magnitude spectrum. And you should know that multiplication in the frequency domain is convolution in the time domain. Similarly, multiplication in the time domain is convolution in the frequency domain. We used many fundamental concepts to introduce FM synthesis and explain how it works. First of all, musical tones have many frequencies or components called partials. Typically, musical tones with a strong perception of pitch have harmonic partials. So in other words, the sinusoidal components are some fundamental frequency F0, and 2F0, 3F0, multiples, in other words. FM synthesis generates a carrier frequency plus multiples of the modulator frequency. So by choosing all of the frequencies and parameters carefully, we can generate tones with a strong perception of pitch by generating harmonics, or we can generate inharmonic spectra and many variations. So we get a rich variable spectrum for the cost of 2 oscillators, and that's a great advantage of FM synthesis. You should know how to design an FM instrument to achieve, at least qualitatively, a desired spectrum. Harmonic partials, many partials, few partials, inharmonic partials, and so on. And you should understand about the modulation index and its relationship to the number of partials that are generated. We talked about algorithmic composition, especially in Nyquist, using patterns and combinations of patterns to do interesting selection of parameters for music generation. We also talked about random selection from distributions and from lists. We talked about guiding the overall form of a composition in various ways, letting the computer to make detailed choices. So you should know how pattern objects work in Nyquist, You should understand the form and the interpretation of Nyquist scores. You should know how to make a score with ScoreGen, this very powerful macro. And you should also understand how to use sref, which, remember, grabs a sample, a value from a Nyquist signal or a Nyquist sound, grabs that sample at any particular time, and you can use sref to incorporate global tendencies into algorithmic choices. Next, we talked about sampling synthesis. High-quality sound from recordings is used to construct notes and do synthesis. There are limits to what you can do with sampling synthesis. You can control pitch to at least to a limited range on any given sample, and you can control duration through looping. So you should know how sampling works to change the duration of samples and how sampling works to change the pitch of samples, and generally how this synthesis mechanism works. We talked about granular synthesis. Granular synthesis is a sound generation processing mechanism that came about with computers. It's very powerful and useful, especially for constructing interesting sonic textures. It chops up sounds to generate these textures. You can use granular synthesis in a very deterministic way to perform a type of time stretching of signals. And you can use granular synthesis with random parameters, random processing, to process or to create turbulent textures. You should know about different grain parameters, the duration, density, time offset in a source file, time offset in the output sound, pitch shift, and so on. And you should know how to use fixed step sizes of grains to accomplish time stretching. We talked about spatial audio. One direction for spatial audio, particularly for headphones, is HRTFs, a head-related transfer function. The idea is to filter sound in the same way that your head would filter sound, and use headphones to eliminate room effects and to isolate the left from the right ear. We also talked in general about cues for direction and distance. We talked about panning, which basically takes advantage of interaural amplitude difference. We talked about interaural time difference, the time delay reaching the left and right ears. We talked about attenuation with distance and the idea that the ratio of reverberation to direct sound is a strong cue for distance. You should know how to use HRTFs. In other words, basically select a left and a right HRTF and convolve with the signal to apply that filter. You should understand about constant power panning versus linear panning. We talked quite a bit about the voice. There are a number of synthesis methods that take advantage of the source filter model. The human voice is really the reason we're interested in source filter models. The human voice can be modeled as a source, which is the vocal folds, plus a filter, the vocal tract. We learned about formants, which are resonances of the vocal tract that can boost the spectrum around certain frequencies, called formants. And the first or lowest two formants mainly determine different vowel sounds. You should know how to use LPC, or spectral processing, for cross-synthesis and what that means. You should know how vowel sounds are made with resonances. Next, we talked about physical models. Physical models attempt to simulate the physics of vibration in order to create rich, natural-sounding sounds. One of the important components of many physical models is the waveguide. The waveguide is a two-directional delay line. So conventionally, we talk about the waveguide having a left-going wave and a right-going wave. And if you want to know what that waveguide is modeling in terms of physics, you sum the left-going wave with the right-going wave to get the simulated signal. For example, the air pressure in a tube. You should know that the waveguide is an efficient implementation of tubes and strings. It's just two delay lines which can be implemented as a circular buffer. You should understand that in a waveguide, there's no signal loss, it's just signal propagation. But if you have a lossy medium, which is always the case in the real world, you can model those losses with a lumped filter representing the entire round-trip loss. And nonlinear elements are used to produce oscillation. If we just bang on a tube that resonates, it'll resonate, but it dies away exponentially. So in a real acoustic instrument or in a physical model of an acoustic instrument, there always has to be some nonlinear element such that models lips or reeds or bow-string interaction if you want to have some kind of sustained oscillation. Next, we talked about spectral interpolation synthesis. The spectrum is conceived of as a function of frequency and amplitude controls, which are the inputs to the instrument. The spectrum is then the output. So this is a model not so much based on the physics of the production of sound, but on the perception of sound, which is generally in terms of the spectrum. Controls like amplitude and frequency depend strongly on phrases and musicianship, and we saw examples of that. You should know the implementation of spectral interpolation synthesis is a modified table lookup oscillator. We have two tables storing different spectra, and we can interpolate between tables. Spectral interpolation synthesis is limited to harmonic spectra because it's based on table lookup, which generates periodic sounds. We talked about data compression, and we branched out a little bit from our narrow confines of computer music to talk about data compression in general because it's an important topic and it all relates back to computer music. We talked about compression through coding redundancy, in other words, how you represent each token or each symbol in a message. We talked about inter-sample redundancy, so in other words, taking advantage of the relationship between adjacent or sequences of symbols, which sometimes become more predictable. And we talked about perceptual redundancy, the idea that we cannot perceive everything that exists in a sound signal, so we can throw out things that are inaudible in order to get higher compression. So you should know about mu law, which is a quasi-logarithmic encoding, and why you might want to do that. Here's a hint. Logarithmic encoding gives you essentially a constant signal-to-noise ratio regardless of the amplitude of the sound. You should know about temporal masking, which is very important in MP3 and other perceptual coding systems. You should know about frequency masking. You should know about encoding in the frequency domain and why do we do it. Here's a hint. The representations in the spectral domain, especially for music, tend to be sparse because not all frequencies are present at every time. And the sparsity of the signal gives us the opportunity to do much better compression. You should understand the role of quantization in audio compression. Basically, we reduce the sample size, which means we have fewer bits, which means we get more quantization. And then this quantization is acceptable if it is masked through masking. So we can essentially, through masking, get away with quantization, which means we have fewer bits to encode, and that's really where the compression comes from. We saw a lecture on music understanding, and I covered in that lecture computer accompaniment, score alignment, style recognition, onset detection, human-computer music performance, which is responsive listening computers in live performance. And you should at least understand what all these terms mean and have some sense of these research directions in computer music. So that's a quick summary of the course. What did we leave out from this course? I'm sorry to inform you that we did not cover the entire field of computer music. There are a few things left. Here are some important picks that I would direct you to think about or learn about or pursue in the future. First of all is real-time systems. We specifically chose to work with Nyquist, which is a non-real-time system because it's a very rich programming environment and it lets you step back and think about what you're doing. And it also lets you model very complex algorithmic composition and build whole complex pieces, which might be very difficult to think about if you're worried about real-time performance at the same time. But real-time systems are very important, very widely used, and standard practice now. From a computer music or an academic viewpoint, real-time systems have some important concepts, including scheduling events, managing and representing time, and how do audio and MIDI systems and their interfaces work. So there's a lot of material there. Another area of research and activity related to computer music is music information retrieval. This area focuses on, for example, audio features. How do we extract information from audio signals? Genre classification. How can we determine whether an audio sample is a rock song or a news broadcast or classical music? And there are many related problems, like, is this song an instance of another song, or was it performed by the same artist, and so on. And then there is music fingerprinting, which is the identification of particular pieces of music from recordings that have perhaps been distorted, noise has been added, and so on. A third area is instruments and interfaces. This has to do with human factors, ergonomics, construction of electronic instruments with using sensors, and how to deal with the sensors and sensing information. How do you take gestures as input and map them to musical control as output? So these are some of the areas that I think are important that I would put on the list for future study. So in conclusion, let's go back to the very beginning of the course, and I said a few words about why I think computer music is interesting. And what does it really do for us? Well, one important concept is that of precision. Computer music gives us the ability to create and refine sounds with precise control. And this is, of course, very interesting to scientists and psychologists because they can make stimuli repeatably. They can perform experiments where one parameter is varied and you can see what that does. But it's also very important for composers. It gives composers the opportunity to focus on the finest details of sounds and to make small changes to those sounds incrementally and be able to reproduce their work so that the degree of refinement is enhanced tremendously by the precision of computing. The second thing is automation, the ability to control high levels of music structure, leaving low-level details to the computer. So we're talking about algorithmic composition and the idea that composition effort can take place at many different levels. And a third thing that I would add, although we haven't really discussed it in this course, is interactivity, the ability to delegate compositional decisions to the computer at performance time. So this is related to automation, but it has this interesting added component that as composers, we do not have to end our role in music making when we hand the score off to performers and they go off on stage. With computers, we composers can actually put our compositional ideas into computers and have the composition continuing to take place during a live performance by interacting with performers. So I think this is also a very interesting idea. It's a new concept in music, or a new capability in music that has really come about with the advent of computers. So I hope that you learn some computer science skills and some music skills that are new to you, and especially how these skills can be combined. So please keep these skills with you and explore them further in your musical future.